Okay.
What do you think? Okay. Okay. So welcome to today's talk. This is the third and final lecture in Bernhard Keller's lecture series in the context of the Rothschild Fellowship at the Newton Institute. The slides for and the videos of the talk are posted on the Newton Institute webpage. If you click on the link to the talk in the program, then you will also be able to see the slides. Furthermore, Bernhard has kindly posted a link to the slides in the chat.
Yeah,
and we will then post today's talk and the slides also on the webpage. So thank you very much, Bernhard. Over to you. Sorry? Yes? Perfectly. Okay. Bernhard, thank you very much for your patience. Everything's
Thank
good.
you very much. Then let's quickly remember what we did last time. So first, at the level of the cluster algebra, we have an ice quiver Q. And associated with this ice quiver, we have the cluster algebra with non-invertible coefficients, which is an algebra over the polynomial ring and the frozen variables. Then we have its localization at all the frozen variables. And then we can specialize the frozen variables to one, and we get the associated cluster algebra without coefficients associated to the ice quiver, where we have removed all the frozen vertices and all arrows incident with frozen vertices. So we get this triangle of algebra morphisms with the localization morphism and the specialization morphism. Now, when we have a Frobenius categorification, then we can categorify this triangle. So the cluster algebra with non-invertible coefficients is categorified by the Frobenius category itself. Then I tried to argue that the localized cluster algebra is categorified by the derived category of the Frobenius category, and the cluster algebra without coefficients is categorified by the stable category of the Frobenius category. And then this triangle lifts to the well-known triangle of functors, the inclusion of the Frobenius category into its derived category. We send every object to the complex concentrated in degree 0. And here we have the well-known projection functor. If we take this modulo the bounded homotopy category of projectives, then the quotient identifies with the stable category. And so this is nice. When we have such a Frobenius categorification, we can faithfully categorify the cluster algebra with its coefficients and with the frozen arrows between frozen vertices. But such Frobenius categorifications don't always exist. Usually there's an obstruction to the existence of such a Frobenius categorification. And the idea is that we need something more general, which works in, well, which should ultimately work in complete generality. For the moment, it works in the relative Jacobi finite case, at least. So this and this thing which should always work is the Higgs category. The Frobenius category is in particular an exact category in the sense of Quillen. The Higgs category is no longer exact or triangulated. It is X-triangulated in the sense of Nakaoka and Pallu, but it is also always Frobenius. Then there is a generalization of the derived category. That's the relative cluster category, which we constructed last time. And then again, we have the generalization of the stable category, well, which is just the Amiot cluster category associated with the reduced quiver with the reduced potential, where we have removed the frozen vertices, the arrows incident with frozen vertices, and all the cycles in the potential which pass through frozen vertices. And we get an analogous get a generalization of this triangle of functors. And the construction is a bit different. Yes, we actually start by constructing the relative cluster category as a direct generalization of the Amiot construction. And then inside we construct the Higgs category as a certain subcategory stable under extensions, which then becomes X-triangulated for the structure induced from this triangulated category. And its Frobenius, its stable category identifies with the cluster category associated with the reduced quiver with potential. And we have decategorification maps here in the Frobenius case, the cluster character associated with a chosen cluster tilting object. Then we have its localized version at the level of the derived category. And here, so today, I will give the analogous construction for the Higgs category. So let me jump to lecture 3. And yes, so one important question, which we briefly mentioned with Matthew Breslin at the end of last week's lecture, is the question of when the Higgs category is actually exact. Yes, so it is always X-triangulated, and some X-triangulated categories are actually exact. And well, if it is exact, then it is going to be a Frobenius exact category. And okay, let me give you the answer. Let's recall the notation. So we have our ice quiver with potential. We have the associated relative Ginzburg algebra and its homology in degree 0, which is the relative Jacobi algebra. Then we construct the relative cluster category as the quotient of the perfect derived category of the relative Ginzburg algebra by the thick subcategory generated by all non-frozen simples. So if the set of frozen vertices happens to be empty, then this is just the classical definition due to Claire-Amiot. But in the general case, it's a bit different. And then inside this category as an extension closed subcategory, we have the Higgs category, which becomes Frobenius X-triangulated. And now, and which is well defined, at least in the Jacobi finite case. Yes, I should have made this assumption already up here. And well, at least in this case, and most probably in greater generality, when the relative Jacobi algebra is Noetherian or even coherent, we have equivalence between these statements. First of all, the Higgs category is exact, and that happens precisely if all inflations are monomorphisms, as we have learned in Jan Palu's talk in Jan Palu's course a few weeks ago. Then, second equivalent condition, the relative Ginzburg algebra is concentrated in degree 0. It is a Stork algebra. Its homology is concentrated in degree 0. Then we can also reformulate this by saying that the Jacobi algebra, the relative Jacobi algebra, is internally free-Calabrian with respect to the idempotent given by the frozen vertices. Yes, internally free-Calabrian in the sense of Matthew Breslin, or one equivalently a certain canonical complex of lambda bimodules is actually a resolution of the identity bimodule. And you can find the definition of this canonical complex, for example, in definition 5.4 of Matthew Breslin's paper, preprint from October 2015. Okay, so yes, so there are ways of, yeah, it's an important question, and there are, I think, good criteria for deciding this, whether it's the case or not. Okay, are there questions so far? There's one thing in the chat. Yes, that's just the link. Okay, so now let's come to the fourth section on mutations, decategorification, and braid group actions. So, well, there are two types of mutations at non-frozen vertices. Yes.
I wanted to mention that there's a question in the room.
Yes.
Ippolito?
Can you hear it?
Now we can hear you, yes.
Now, okay. All right, it was just a question of attribution. I got this complex from Broomhead, who got it from Ginsburg. And
yes. Yes, sorry. I did mention Ginsburg. Yes. Yes. Thank you. Okay, let's. Yes. So. Yes. And it's also in a paper by Yama, Rayton, and others. But anyway, Ginsburg. Yes, and I think that's. Thank you. Yes, so we can mutate at non-frozen vertices. And in some cases, we can also mutate at frozen vertices. That will also be useful. So first, mutation at non-frozen vertices. Okay. Well, first at the purely combinatorial level, we take an ice quiver with a frozen subquiver F. Yes, for example, here, this frozen subquiver in this 3 cycle. And then there is an extension of Fomin-Zelewinsky's original rule, which applies to the case where F is empty, or to the case where we neglect arrows between frozen vertices. So here, the new thing is that we don't neglect arrows between frozen vertices. So we choose a non-frozen vertex and we mutate in the usual way. Yes, so we add new arrows for the paths of length 2 passing through the mutating vertex. We reverse all arrows with source or target the mutating vertex. We remove a maximal collection of non-frozen 2 cycles, and then we choose a maximal collection of half-frozen 2 cycles, like this, and we replace each of these half-frozen 2 cycles by a frozen arrow in the direction of the non-frozen arrow in the 2 cycle. Okay, so this is a new reduction step. So if we do this in this simple example, yes, so well, we follow the rule step by step, and then the 3 cycle is transformed into a 3 cycle again. Whereas if we just pretend that nothing is frozen, then the 3 cycle is of course mutated to this chain. Okay, so it's something different, and it does occur in nature. Yes, when you use Frobenius categorification, then this is the way the quiver will mutate, with the frozen arrow being reversed instead of eliminated. Okay, and now this lifts to the algebraic level. So now we add a potential into the picture. A possibly infinite linear combination of cycles of length at least 3. For example, here we can just take the potential ABC. And then Matthew President has extended Dirksen-Bäumann-Zelewinsky's work for the case without coefficients to the case with coefficients and arrows between frozen variables. So the mutation operation on ice quivers admits a good extension to ice quivers with potential, in the sense that the underlying ice quiver of the mutated ice quiver with potential is given by the purely combinatorial rule, and this holds at least if W is generic. Okay, so in this example, well, we can go through the process, and then we get the expected potential, yes, which is well, just the reverse potential. Okay, and now this lifts to the categorical level. So we take an ice quiver, let's say with generic potential, and then remember we have the associated Ginzburg morphism. Let me recall the example. Yes, so we take this simple example. This is the frozen subquiver. Then we have the algebra pi and the relative Ginzburg algebra gamma. The algebra pi is just the two-Calabi-Yau completion of the path algebra of the frozen part. So it looks like this. Yes, we add arrows in the opposite direction, which are still of degree 0. We add two loops of degree -1, and the differentials of these loops give us the preprojective relations, so that homology in degree 0 is the usual preprojective algebra. Here for the Ginzburg algebra, well, we add now arrows in the opposite direction of degree -1. For all the non-frozen arrows, we add a loop of degree -2 for each non-frozen vertex. And the differential, well, the differential of the new arrows is given by the cyclic derivatives, and the differential of the loops is given by commutators between old and new arrows. And then we have the Ginzburg morphism, which takes, well, which is given by the inclusion at the level of the given frozen arrows, and at the level of the reversed arrows, it is given by the cyclic derivatives of the potential. So here the cyclic derivative of the potential with respect to C gives us AB. So this reversed arrow is taken to this composition AB. Yes, and this, of course, works in complete generality. And now let's take again a non-frozen vertex. Then we have an associated simple differential graded gamma module. And well, the algebra gamma is not in general a Calabi-Yau algebra, but the Ginzburg morphism has a relative Calabi-Yau property. And thanks to the relative Calabi-Yau property of the Ginzburg morphism, the non-frozen simples are still three spherical objects. So their homology, sorry, the Yoneda algebras are the homology algebras of a three-sphere, yes, just K plus another copy of K in degree +3. And we have this cell duality for morphisms with source, the simple module. And then whenever we have a spherical object, we have the associated spherical twist functor, which can be computed at least on objects using these natural triangles. Yes, we look at morphisms from the simple to some object X, and then we have the evaluation morphism for such, and its cone gives us the image of the object under the twist functor. Okay. Now we mutate our ice quiver with potential. We get another ice quiver with potential Q prime, F prime, W prime. We get another two Calabi-Yau completion and another Ginzburg functor. We write Pi for these cofibrant modules. And then Yilin Wu shows in his thesis that as in the classical case without coefficients, we have two triangle equivalences between the derived categories of the Ginzburg algebras, which take all the pi's to, sorry, actually it's pi primes, sorry, pi prime is taken to pi for all I different from the mutating vertex, and pj associated with the mutating vertex is either taken to the cone, the homotopy co-fiber of this canonical morphism, or for the plus version, or to the homotopy fiber of this canonical morphism for the minus version. And these functors differ only by composition with a spherical twist functor. And moreover, the new Ginzburg algebra is concentrated in degree 0 if and only if that was the case for the original one. Okay, so in particular, so the Higgs category for the original ice quiver with potential will be exact if and only if that's the case for the new one. And okay, now suppose that we are in the relative Jacobi finite setting. Then remember the defining diagram for the Higgs category. Yes, so this is the defining exact sequence for the relative cluster category. And in here we have the fundamental domain formed by the cones over the morphisms between objects in ad of gamma. The hom pi is surjective for the frozen eyes. And by definition of the Higgs category, it's the image of F, and it turns out to be k-linearly equivalent to F and extension closed in the relative cluster category. And then, well, these two functors, phi minus and phi plus, differ only by composition with a twist at a non-frozen vertex. And you see that, well, an object X and its image under the twist functor only differ by a direct sum of possibly shifted copies of this non-frozen simple. And that means that the two functors, phi plus and phi minus, induce the same equivalence in this quotient. Yes, so just because they only differ by a twist with respect to a non-frozen simple, this difference becomes 0 in the relative cluster category. So here we get an induced functor, a unique induced functor, unique induced equivalence between the two relative cluster categories. And then it is also easy to see that it will not induce an equivalence between the fundamental domains in general, but it does induce an equivalence between the two Higgs categories inside the Frobenius categories. Okay, so if we call T the image of gamma in the Higgs category and Ti the image of Pi, well, then we can define Tj star and the mutated cluster tilting object in the usual way, and we will have the usual exchange conflations. And by more or less by construction, the ice quiver of the endomorphism algebra of this mutated cluster tilting object is given by Matthew Preslin's mutation rule. Okay, so this is in complete analogy with the situation which we have in Frobenius categorification and in stable, let's say in stable Frobenius categorification, or in categorification via cluster categories, except that now the frozen arrows are taken into account. Okay, so this is mutation at frozen vertices. Now, sorry, at non-frozen vertices. Now let's look at mutation at frozen vertices. So this is an operation which was discovered by Chris Fraser and Melissa Sherman-Bennett in their study of cluster structures on positroid varieties in June last year. And it turned out to be very useful for this, and I think it is useful more generally. So let us again take an ice quiver and now a frozen vertex. Now we cannot take a frozen vertex in an arbitrary frozen vertex. We have to have a certain local configuration around the frozen vertex. Namely, it should either be a frozen source, which means that it's a source of the frozen subquiver, and it does not have any outgoing non-frozen arrows. So the non-frozen arrows incident with this vertex are all incoming. So it looks, locally it looks like this, or dually it can be a frozen sink. Okay, and then then we can first define a mutation at the purely combinatorial level by essentially the same rule. Yes, so only in the first step, yes, in the first step, we may have such subquivers, and then, well, we have to take the composed arrows, and the composed arrow is necessarily non-frozen because its source is non-frozen, or its target is non-frozen. Sorry, I forgot this second possibility here. Or yeah, in the second possibility, I is frozen and K is non-frozen. Okay, and the rest of the rule is exactly the same as for mutation at non-frozen vertices. Okay, let me show you an example. So in the latest version of the applet, frozen mutation at frozen vertices is implemented. Okay, so here you have this example which is associated with the Grassmannian of planes in four-dimensional space. And well, as you can see here, the frozen vertex number 1 is a frozen sink. It's a sink for the frozen subquiver, and no non-frozen arrows arrive at 1, so we can mutate here. Click. And now you can see that 4 is a frozen sink as well, so we can mutate here. Okay, and now, well, it's the effect, the overall effect was the passage to the opposite quiver. And there is another possibility for passing to the opposite quiver, namely we can just do a non-frozen mutation at the vertex number 3. Okay, so in other words, yes, sorry. In other words, yes, so here. So we start from this quiver, this ice quiver, and performing these 2 frozen mutations has the same effect as performing 1 non-frozen mutation. So if we compose all these, then we get an automorphism, well, an automorphism of this frozen of this ice quiver. Yes, more precisely, well, if you like, an element in the modular in the cluster modular group of this ice quiver. But actually, it will not be in the cluster modular group. It will be in a slightly bigger group, namely it will be in the group of quasi-cluster automorphisms of the corresponding cluster algebra. So this is a method for constructing quasi-cluster automorphisms, and we will see that a bit later. And so this was for the moment at the combinatorial level. And well, Matthew Preslin's work also shows that mutation at frozen vertices also has a good extension to ice quivers with potential. And then we can lift it to the categorical level. So we take an ice quiver with potential, we mutate, say, at a frozen source. And then we get a triangle equivalence, this time only one triangle equivalence. Yes, we will denote it by psi plus if we mutate at a frozen source, and by psi minus if we mutate at a frozen sink. And it is given in this way: the pi primes for I different from j are sent to pi's, and the mutating frozen pj is sent to the cone over this natural morphism. And by assumption, all the arrows going out from J are frozen arrows and have frozen targets. So these are just our other frozen PKs. Okay, so we get this, yes, equivalence. And we get a commutative diagram which shows us that, well, here we have the inverse twist functor at Sj. Sj is a simple over this 2 Calabi-Yau completion. Now the 2 Calabi-Yau completion is 2 Calabi-Yau, therefore this simple is a 2-spherical object, and we have an associated twist functor. And what we have done is we have extended this twist functor to an auto-equivalent, sorry, to an equivalence between the corresponding perfect derived categories of the Ginzburg algebra. Okay, and this induces an equivalence in the relative cluster categories, but this equivalence, in contrast with mutation at non-frozen vertices, this equivalence does not take H prime to H. Okay, so it will change the position of the Higgs category inside the relative cluster category. Yes, so we cannot expect it to induce an isomorphism between the corresponding cluster algebras, but it does yield a quasi-cluster isomorphism. Yes, and it's a very simple quasi-cluster isomorphism. Yes, it takes all the variables xi prime to the variables xi for I different from j. In particular, all the initial non-frozen cluster variables are taken to initial non-frozen cluster variables. It's only changed this unique coefficients to this expression. Mm-hmm. Yes. So, are there questions so far? That doesn't seem to be the case. So, let's come to decategorification. So again, we take a Jacobi finite ice quiver with potential. We have we keep the same notations as before. The stable category of the Higgs category is the cluster category associated with the reduced quiver with potential. We number the vertices in the conventional way. And then, well, we have a canonical cluster character at the stable level. And we can lift it to the non-stable level in a simple way. Namely, well, so here, this is the situation. Yes, we have the stable category of the Higgs category, which is the usual cluster category, where we have the usual cluster character with values in the Laurent polynomial algebra without the coefficients. here we have the relative cluster category, and what we would like to do is to define a cluster character at this level of the relative cluster category. And then by restriction, it will yield a cluster character on the Higgs category. And so what one can show is that indeed there is a unique map such that this square commutes and three conditions hold. So first, a normalization condition, if we take an object without non-zero direct summands in P. Yes, so P is the subcategory of projective injectives in H. And then we can obtain the corresponding cluster character by taking the stable version and multiplying with the corresponding component of the G vector, which is defined via an index in the usual way. Then, so this defines it on objects of H without projective injective summands. Then for an object P in the thick subcategory generated by the projective injective summands, yes, subcategory generated inside the relative cluster category, we can compute it simply by looking at the class in the Grothendieck group. And finally, if we have an object which occurs as such an extension, then we can compute it we can compute its cluster character by such a multiplication formula. Okay, yes, and so in this way we get this cluster character defined on the relative cluster category. And this allows us to categorify quasi-cluster morphisms. So if we have a quasi-cluster functor and an algebra morphism, which makes this square commutative, then the algebra morphism is a quasi-cluster morphism in the sense of Fraser, and I gave you the definition last time, I think. And in particular, well, if we can apply this to the equivalence associated with a frozen source, and then we have this equivalence at the categorical level, which lifts the very simple quasi-cluster isomorphism, which I have written down a few slides ago. Okay. And now we can use this to construct group actions. It's not quite precise to say that they're braid group actions, and then in general they will be actions by suitable subgroups of braid groups. Okay, so let's take again an ice quiver with potential. We have the corresponding Ginzburg functor, and the source of the Ginzburg functor is, yes, and let's say Ginzburg morphism. Okay, so its source is this 2 Calabi-Yau DG algebra, and the simple modules associated with the vertices become two spherical objects in the derived category, and so we have the twist functors now in dimension 2 instead of 3, with the same defining triangles, and by an old theorem by Seidel-Thomas, I think from 2000, we get a weak action of the corresponding braid group on the derived category, weak action which takes the braid generators to the spherical twists. Yes, so the braid group is just defined in this way. If there is no arrow between I and J, they commute, and if there is exactly one arrow in F, yes, actually it can go in either direction, then we get this braid relation. Okay. Now, suppose we have an element of this braid group, and so we get an autoequivalence. And well, suppose that we can extend this autoequivalence to an autoequivalence of the perfect derived category of the Ginzburg algebra. So what we would like to do is to define an assignment from sigma to such an extension in such a way that, well, I mean, not every sigma will admit such an extension, but we would like that those sigmas which admit such an extension form a subgroup which will then act on the perfect derived category of gamma by quasi-cluster autoequivalences, and therefore on the corresponding cluster algebra by quasi-cluster automorphisms. And the main problem is that if there is such an extension may exist, but we cannot expect it to be unique in general. Yes, but if it is unique, yes, if we have a unique phi sigma making this square commutative, yes, and we look at then these sigmas will form a subgroup of the braid group, and this subgroup will act by autoequivalences. Okay, so we would like to have a sufficient condition for such an extension to be unique. Okay, and the motivating example, yes, sorry. Let me remove this. So before giving you the condition, let me point out the motivating example for this situation. The motivating example is Chris Fraser's affine braid group action on the Grassmannian, more precisely an open cell in the cone of the Grassmannian. So for example, in the Grassmannian of 4-dimensional subspaces in 8-dimensional space, we have this quiver with potential. So you can see its frozen subquiver is just such a cycle, and the pi, well, pi is the Calabi-Yau completion of the path algebra of this, and since this is non-Dynkin, this Calabi-Yau completion is just the usual pre-projective algebra. And then the braid group is the affine braid group on D strands. It acts on this perfect derived category. And it turns out that indeed there is such a subgroup inside which is generated by products of braid generators. Namely, we take products of generators which are at least which are distant by, which are not neighboring, yes, which are not neighboring, and in fact they are distant by D, the greatest common divisor of K and N. And this subgroup turns out to act by autoequivalences on the perfect derived category and by quasi-cluster automorphisms on the Grassmannian. So this is the situation which we would like to generalize. So in this situation, for this quiver and for these specific elements of the group, we do have such a commutative diagram, and the corresponding automorphism, autoequivalence, which we get here, does induce the braid group action on the cluster algebra. Okay, so this is the motivating example, and now, yes, I have already said this. Yes, so in general, this extension will not be unique, and we need a sufficient condition to ensure this uniqueness. Okay. Now, And we also need a sufficient condition for it to be a quasi-cluster auto-equivalence. So, and this will involve some reachability condition. So to formulate this reachability condition, notice that if we have such a diagram, then we also have the right-hand part here. Yes, yes. So this phi sigma will automatically, thanks to the commutativity here, it will automatically induce an equivalence between the relative cluster categories and in the stable categories of the Higgs categories, not between the Higgs categories themselves, but between their stable categories realized as quotients of the relative cluster category. And then we say that an autoequivalence, such an autoequivalence, for example, is a quasi-cluster autoequivalence if it takes the image of the Ginzburg functor to itself, and the induced functor here takes the initial cluster tilting object to a reachable cluster tilting object. Okay, so this is the reachability condition which we need. And now here are the conditions which will ensure that the extension, if it exists, is unique. So, well, first of all, a finiteness assumption. And so here I formulated with finite dimensional lambda because that's the setting where it is proved for the moment, but you can most probably extend it to the case where lambda is Noetherian or coherent. Then we assume that the Higgs category is exact, not just X triangulated, but exact. And we have seen the criteria for this before. So it means, for example, that the relative Ginzburg algebra is concentrated in degree 0. And if you like, you can view this condition as a condition which says that we have enough frozens. Okay, and then we need another condition. So, for example, a sufficient condition would be that this morphism is surjective. And this means that we have enough rows and arrows. Now, this surjectivity does not hold in examples we are particularly interested in, namely the positroid varieties. But what still holds is that we get an epimorphism of algebras over the center of H0 of pi, over the preprojective algebra. Okay, so this is weaker, but enough for our purposes, and it still holds for the examples of the positroid varieties. And then, in that case, indeed, we can show that the extension, if it exists, is unique up to, well, it should, of course, be an algebraic triangle equivalence, and then it will be unique up to algebraic isomorphism. Yes, an algebraic triangle equivalence is one given by a bimodule, and an isomorphism is an isomorphism in the derived category of bimodules. Okay, and then we can look at the subgroup of the braid group formed by the sigma admitting such an extension, which is unique, and this subgroup will act by algebraic autoequivalences on the perfect derived category. And if we now restrict to the subgroup of this U tilde, where the image of the initial cluster tilting object in the stable Higgs category is reachable, then this action will decategorify and induce an action of the group U in the cluster algebra. Okay. And there is a combinatorial recipe for how to realize this in practice, yes. So we suppose that we can realize our braid group element by a sequence of braid generators such that each one is a frozen sink or source in the corresponding mutation at the previous frozen vertices. Yes, this is not always satisfied, but it turns out, I mean, it is definitely satisfied in the case of the Grassmannian and most probably also in the case of the positroid varieties. And then we assume, so here we have a sequence of frozen mutations. And now we assume that we can compensate the action of these frozen mutations by a sequence of non-frozen mutations. So we take our ice quiver, we apply first the frozen mutations, and then we assume that we have a sequence of unfrozen mutations which undoes the effect of these. So we get an isomorphism between the result of this composed operation and the original ice quiver. Okay, and then then this will define an element of our group U, and the required quasi-cluster automorphism is given by the corresponding composition now interpreted in the cluster algebra. Yes. So if you, I mean, what happens at the, it's useful to think of the effect of these operations on the cluster tilting object. Yes, imagine that this is the initial cluster tilting object with frozen vertices 1 and 2. Then we do frozen mutations at 1 and 2. It will be transformed into this cluster tilting object. And then we can perform mutations at 3, 4, and 5 to transform it into this cluster tilting object. And then there's an auto-equivalence taking this cluster tilting object to this cluster tilting object. So that's the very simple idea. Yes, so we first have the sequence of non-frozen mutations, and then we can undo its effect on the ice quiver by a sequence of unfrozen mutations, and the composition gives us the automorphism. And here so this is the example of the Grassmannian of two-dimensional subspaces in four-dimensional space. This is a very simple, very small example. Yes, so here the braid group is the braid group associated with this quiver diagram, and the subgroup is just isomorphic to Z, and it will act by quasi-cluster automorphisms in the corresponding cluster algebra with invertible coefficients. And it turns out that what we see here and what also works in general for the Grassmannians generalizes to open positoroid varieties. And okay, so and I'd like to stop here. Thank you very much.
Okay, well, thank you very much, Bernhard, for this lecture today and for all 3 lectures. It was really wonderful. Are there any questions?
Correctly, so
Sorry, could you repeat that, please?
In the case that H is exact, is it right that the relative cluster category is just the derived category of H?
Yes, that's true. Yes, yes.
Right. So in this case, me taking in a frozen vertex, derived equivalent.
Sorry, couldn't hear that.
Yes, I mean, mutation at a frozen sink or frozen source will yield an auto-equivalence of the derived category. Yes, of this Frobenius category. Yes.
But I can think of it as replacing H by a derived equivalent.
And you can think of it as replacing H with a derived equivalent. Yes. Yeah. Yes. Yes. If you like. Yes. 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 Yes, and I mean, so in the case of an auto equivalence, yes, it will, it's like a tilt, yes, a tilt of the heart, only that the heart now is an exact category and not a Frobenius category, if you like. I mean, the situation is very analogous.
I have a question.
Yes.
Nobody else has one. So maybe you said that and I missed it, but the functor from the relative cluster category to the stable Higgs category,
Yes.
what is that functor?
Yes. Let me write it down. I mean, like maybe it's.
I mean, if the category is not exact.
Yes. Okay, let me write it down. So we have the perfect derived category of gamma, and we have the subcategory generated by the non-frozen vertices, and we have the relative cluster category, and here we have the perfect derived category of pi. And okay, this is not in general this is not in general a fully faithful functor, but nevertheless you can take the Verdi quotient by its image, and if you take the Verdi quotient by its image, you get the perfect derived category of the reduced quiver with potential. And inside you have an equivalent copy here, and also so you can complete the diagram like this, and then it turns out that these two are the same. So here you get, on the one hand, so here you get C of gamma bar. Yes, this is the same as what was previously denoted by DFD of gamma bar. Okay, and inside, so now to complete everything, so inside this category we have the fundamental domain, which is k-linearly equivalent to the Higgs category, and the stable category of the Higgs category identifies with the cluster category of the reduced quiver. Okay, and now 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 I think it should be clear. So this composition, if you like, is the functor you were looking for, I think.
I see. Okay. Yes. Thank you.
Yes. And in the Frobenius case, I can write down the analog categories in the Frobenius case. Let me write them, let's say, in orange. So in the Frobenius case, this becomes the derived category of the exact category. Sorry, no. So this becomes the derived category of the exact category. This becomes the exact Frobenius category itself. This, of course, becomes its stable category. Then this becomes the perfect derived category of, let's say, A, where A is the H0 of the Ginzburg algebra, or so this contains T, and then A is end of T. And A is actually of global dimension 3, so it is also the bounded homotopy category of the projective modules over A, if you like. Okay, or let me see, sorry, let me write it yet in another way. It is also the bounded homotopy category of the additive subcategory generated by T. Yes, let's write it in that way. And then this becomes the subcategory of acyclic complexes, acyclic in E complexes of direct factors of finite direct sums of copies of T. And this, yes, yeah, I think this is the dictionary, yes. And the image, yes, maybe the image of this functor is then the bounded homotopy category of projectives inside the derived category.
Okay, that's
Yeah.
very good. Thank you. That's very helpful.
Maybe I will include that in the notes. And
That's a good idea.
Copy.
Are there any other questions?
Yes, and I will also. I think I have not yet updated the copy of the applet for download, but I will also do that so that you can do your own mutations at frozen vertices.
Excellent. Okay, well, if there are no other questions, then let's thank Bernhard for these lecture series. Thank you very much.
Thank you very much.